notebooks out and stuff. Also, go ahead and get like 3 or 4 index cards for your exam notebook out, because we're going to fill a couple of those out today too. These won't be for the exam on Friday, but for the next exam. So you don't need to bring them on Friday, but keep them. So I have found that probabilities are one of those things that do not come intuitively to me. When there are simple cases like coin flips or throwing dice, it's very easy to visualize these things, so it's rather simple. But as we're going to see today, probabilities can get complex very quickly. Sorry, I just ran. Yeah, right? Man, I'm out of shape. Okay. So I found there are 2 questions that can get me through any probability problem. So in those times when I'm taking an exam and I find myself confused or baffled by a question, I ask myself these 2 questions. I ask myself these 2 questions. And the first question is, how many possibilities are there? Number of possibilities. And the second question is, out of those possibilities, how many meet my criterion? Number that meet criterion. And I'll explain what I mean by criterion in a moment. But if you get these 2 numbers, you create a ratio or proportion. And if you simplify that ratio, what you will get is a number between 0 and 1, and that number represents the probability of finding something which meets this criterion in a set of possibilities. So what do I mean by criterion? I have a dice. It's a 6-sided dice. Denise,
Yes.
how many possibilities are there on a 6-sided dice?
6.
6 possibilities. And if I tell you that the criterion I'm searching for is that the roll be a 1, how many of those possibilities meet that criterion?
6?
If I ask you the criterion is just the roll be a 1, how many?
Yeah.
Go ahead. 1, exactly,
Yes,
right?
sorry.
Because no, it's okay. One out of those 6 possibilities meet my criterion. Thus, the probability on a dice roll of throwing a 1 is about 1 in 6. All right. What if my criterion is that the number be an odd? Well, Heather, can you throw that one at me? If there's 6 possibilities, how many of those possibilities are odd? 3 out of 6. And so the probability of throwing an odd roll on dice is 3 out of 6, or 1/2. I have one more example. Does anybody want to see another one with a dice roll? Okay. Let's make it a little bit more abstract. Because like I said, dice rolls are pretty easy to visualize. Let's draw some pictures. I have a box. And in this box, there are 4 objects. There are 4 objects in this box. How many possibilities are there? If I reach into this box and I grab one item randomly, how many different items could I possibly grab?
4. There's 4 different ones.
4?
There's 4 different ones.
There's 4 different ones, exactly. These questions are really basic, guys. They're not tricky at all. There's 4 items in the box. There's 4 possibilities. Now, if my criterion is that that object be blue, how many of these objects or possibilities meet that criterion? 1 out of 4. What about if that object be pointy?
2.
How many of these objects have points on them?
3.
3 out of the 4 possibilities. What about the probability that it be not pointy? The exact opposite of that.
1.
1 out of 4, 3 out of 4. Notice that if you sum all of our possibilities together, what you get is 1. That's a key rule in probabilities. These are what we call rational probabilities. You can deduce them just by this simple algorithm that I showed you. Identify the number of possibilities, figure out how many of those possibilities meet your criterion, and then simplify the ratio. It'll get you through any probability problem. Even the binomial probability trees that Dr. Lilly was talking about on Wednesday can be understood in this framework. Each path that you take in that tree is a different possibility. And a subset of those paths meet your criterion, that you win twice and lose once. You can still understand it in that framework. Rational probabilities can be pretty simple, but like I said, they get more complex. And the first example of that is conditional probabilities. So take out one of your note cards and write on that note card this statement. The conditional probability of A given B. I'm going to spit formulas at you guys, and I'll explain them in a moment. Just copy the formula down on your note card and then wait. It's the probability that A and B occur together divided by the probability of B. Let's return for a moment to this example. Number that meet criterion divided by number of possibilities. You can think of this thing more generally as a ratio or a proportion. And it turns out proportions are really handy when we're trying to understand probabilities, even as they get more complex. And if you look at the format of this, the structure of this expression, and you look at the structure of this expression, you might notice that they're both ratios. So the question is then, what does this ratio represent? What does the top represent? What does the bottom represent? Well, we know that A and B are events, right? A and B represent events. And these events could occur together, alone, or not at all. And we can imagine a world where all of these possibilities are taking place. Sometimes A occurs by itself, sometimes B occurs by itself. Sometimes A and B both occur, and sometimes neither of them occur. What the top part of this ratio represents is the number of times that A and B occurred together. So how frequently A appears in the presence of B. And the bottom part of this ratio represents how frequently B occurs, period, with or without A. So think about this for a moment. What this is telling me is, out of the times that B occurred, how often was A there as well? And that's kind of what's captured in a conditional probability statement. Because in a conditional probability statement, it tells us B is given. You're given B here. So you've been told that B has already occurred. It changes the probability, or sometimes it changes the probability of A occurring. And in those cases, we would state the probability of A is not equal to the probability of A given B. What's an example of this? Okay. If I asked you to guess my birthday, we have an event A, which represents you being correct. And the probability of that event, if you just took a random shot in the dark, is about 1 in 365. Does everyone see where I got that from? There's 365 days in a year. If you pick one randomly, it's going to be about 100 or 1 in 365. But what if I give you the fact, or a second event, B? What if I tell you that my birthday is in October? So we have this second event, which is that you know my birthday is in October. Well, we can write this statement as the conditional probability of A given B. And as we'll see, the probability changes. Can anyone take a stab at this and tell me, if you know my birthday is in October and you pick a random day, what's the probability that you'll be right? 1 out of 31, exactly. So what we've shown here is that the probability of you being correct changes when you have access to certain information. And that is what is captured in conditional probability statements. Once you understand that, these problems are really easy to solve, at least for your textbook. most difficult part with the problems that are given in your textbook is identifying the type of probability that you need to capture. And one way you know that you're dealing with conditional probabilities is that the question is phrased this way. So let's just say event A is that your boss arrives late. And event B is that your boss arrives by train. So we can imagine a world where this boss is going to and from work every day, and some days she takes the train, and some days she drives her car, some days she bikes, or whatever. And on some days she's late, on some days she's on time. And then there is a set of those days when she both took the train and was also late. Let's think for a moment, let's imagine that this train, that this city that we live in, has a notoriously congested public transit system. So people who take the train tend to be late. The conditional probability that the boss arrives late, given that she took the train, is different than if we don't know that she took the train. Because if we know she took the train, well, we can use that information. We know that people who take the train tend to be late. So the probability of her being late should go up. And let's see, well, in the example I have, it actually goes down, but that's only because of the way I phrased the question just now. It can go either way. I'm going to show you guys right now. So probability of event A is that the boss is late. All we do to solve this problem is plug our numbers into this equation. And they're given to you in the text. It tells you the probability that the boss is late and arrives by train is 0.2. And the probability that the boss is late, period, is 0.4. And when we simplify this, we get 1/2. So the conditional probability is 1/2. The raw probability, or just the probability of A alone, is 0.4. They're different values. And that brings us to the concept of independence and dependence. We say that two events are independent of one another when the probability of A given B is equal to the probability of A. So what I'm saying here is that if you know B, it doesn't change your estimates of the probability of A. An example of this is a coin toss. What's the probability of heads in a coin toss? 1/2. And if I asked you for the probability of the heads, given the last 3 rolls were all tails, what would you say the probability of the heads was? Does the number of tails change the probability of it being a head? No. I can flip a million tails in a row, and assuming that it's a fair coin, I mean, that would be infinitely unlikely, but assuming it's a fair coin, on my next flip, the probability of the heads is still 1/2. So whether or not I know the existence of the 3 tails or I don't, the probability of the heads is 1/2. Thus, coin flips are independent events. All right, what about dependent events? Well, it's the exact opposite. All you have to show for a dependent event is that these two things are not equal to one another. So let's say, as an example, that event A is winning a race. And if you don't know anything about your racers, and there's 3 of them, and you pick one racer randomly, you've got a 1/3 chance of being right. That the racer you pick wins the race. Now imagine a conditional probability for event B, which is knowledge of the race places when the race is halfway over. No places. So this race starts, and halfway over, you now get to pick who you think is going to win. Well, now you have access to this additional information that's represented in which place the races are in, and if you pick the racer that's in first place, you're now going to be more likely to win. So we can say pretty confidently that the probability of A given B is more than 1/3. Because you can make a more educated guess once B is given. So this is an example of two dependent events. Your estimates of who's going to win the race changes when you have B, when B is known, or when you know what place your racer is in halfway into the race. Does that make sense to everyone? The key here is that these probabilities interact with one another. Once you know one, it changes the other one. I didn't get any reassurance from that. Is that
You're good.
You're good. Okay. Thank you, Ryan.
It is 8 o'clock in the morning. So
It is 8 o'clock in the morning. Yeah.
Stuff to speak up.
All right. So let's do some problems from the book with dice rolls. All right. Event A is rolling. My roll is divisible by 3. Event B is that my roll is less than 4. We're going to assess these two as conditional probabilities and ask ourselves, if I don't know anything, what's the probability of throwing a roll that's divisible by 3? And then we tell ourselves, if we know the roll is less than 4, what's the probability that the roll is divisible by 3? And we're going to see that those two probabilities are actually the same. And to figure this out, we can use a very handy thing called a picture. Humans are visual creatures, and if you can use vision to help you understand something, then you should absolutely do it. What I've drawn here is called a sample space. And the concept of a space is very common in mathematics. And what it basically means is the set of all possibilities. So think back to the ratio that I discussed at the beginning of class today. How many points are there in this space? So how many possibilities are there? You might notice that I'm actually asking you guys the exact same questions I asked you earlier, but now I'm giving you this picture as a framework to understand it. Now, if I tell you that the roll is divisible by 3, that's my criterion, that the roll be divisible by 3. How many of these 6 possibilities meet that criterion? 2? These 2 right here. 2 out of 6. So the probability of A, just off the bat, without any knowledge of B, is 1/3. All right, now let's look at the conditional probability. What if I tell you that the roll is less than 4? What does that mean? Well, it means that we restrict our search to only those rolls that are less than 4, which are these 3 guys right here. So these are the 3 possibilities in the space that are left available once we've constrained it to be less than 4. And we ask ourselves the same question again. Given that our roll is less than 4, or given B, what's the probability that the number you choose is also divisible by 3? So let's ask ourselves this question. In this subspace, how many possibilities are there?
6.
In the overall space, there are 6 possibilities. And this is where conditional probabilities come, where they begin to make sense. is because in the overall space there are 6 possibilities. But once you've been given B, once I've been told that my roll is less than 4, I immediately eliminate 3 of those possibilities. 4, 5, and 6 are not less than 4, so they can't be my roll. What's going on here is basically I have thrown a dice, and I put it behind me, and I asked you, what's the probability that my roll is less than 3, right? And then you tell me, it's 1/3. I'm sorry, divisible by 3. The probability the roll is divisible by 3, and you tell me, it's about 1/3, okay? And then I peek at my dice, and I tell you, but the roll is also less than 4. So what's the probability that it's divisible by 3? Well, 6 is no longer an option, because 6 is greater than 4. There's only 3 possibilities left. Does everybody see that? I've eliminated 3 of the possibilities by telling you the roll is less than 4. So only 3 remain. So how many possibilities are there? 3 possibilities. And out of those 3 possibilities, how many of them meet my criterion that the roll be divisible by 3? 1 out of 3. And it's this guy right here. And you might also notice that if I circle both of my groups, the number that I'm interested in is the intersection of those 2 things. Just an interesting observation. But what we've just computed is the conditional probability of A given B. And it turns out they're the exact same. So are these events dependent or independent of one another? Think back to our test. We asked ourselves, is the probability of A equal to the conditional probability? And if they are equal, then they're independent events. And if they're not, then they're dependent. So we've just shown the probability of A is 1/3, and the conditional probability is 1/3. So are these independent or dependent events?
Dependent.
Independent events. Is that what you said, or you said dependent?
I think I might have said dependent.
You might have said dependent? Well, the difference is that dependent events are not equal to one another. So let's see an example of that. What we just did here is we show that these 2 events are the 2 probabilities are equal, so they are independent events. And you might think to yourself, well, they're dice rolls. Of course they're independent. It's just like a coin. But it turns out that's not always the case. So let's take a look at another example from a dice roll, where the events are dependent upon one another. Now my roll is odd. So my event A is the roll is odd. And event B is that the roll is less than 4. So I'm going to draw my little sample space again with each of the 6 possibilities. And now we're going to figure out the probability of A, because that's the first part. In order to answer this question of are these 2 things equal, first we need the probability of A. So let's find it. How many possibilities are there? 6 possibilities. And out of those 6 possibilities, how many meet my criterion that the roll is odd? 3. These 3 right here. So we can conclude that the probability of A, or the probability of rolling an odd number, is 1/2. Now let's take a look at what happens when we restrict that search only to those numbers that are less than 4. So again, I'm restricting my search only to those numbers that are less than 4. And by doing so, I eliminate 3 of my possibilities. So now how many possibilities are there?
And still have to be odd, right?
No, but right now we're just looking at the probability that the roll is less than 4. So there's three possibilities here. And out of those 3 possibilities, how many meet my first criterion? 2 out of the 3. So what we've just computed is the conditional probability of A given B. And we show that it's 2/3. And now we can assess this inequality. Is the probability of A equal to its conditional probability? No, they're not. They're not equal to one another. So are these events dependent or independent of one another? Say it more clearly, because it's hard to tell the difference between 2 words. Dependent. Thank you very much. Yes.
So you said the conditional probability, right?
Yes.
And that would be like a question for either independent or dependent?
Yes.
Oh.
You use conditional probabilities to determine if events are dependent or independent of one another.
Okay.
Right? In conditional, the word conditional basically means what's the probability of A when certain conditions have been met? And those conditions are specified by B. So what's the probability of A? Rolling an odd number. Well, that's 1/2. Well, if I tell you the roll is less than 4, I've now given you a condition. The roll is also less than 4. Now what's the probability? And it's only 2/3, or it's now 2/3, which is different. So they're dependent events. All right, get out your another index card. I'm going to spit another formula, you guys. I'm also going to keep a tally of the formulas that we've talked about today. So the first one is this basic ratio rule that I've taught you. The number of the meet criterion divided by the number of possibilities. The second one that we talked about today are conditional probabilities. So you should have a card that completes that statement. Next, we're going to talk about this idea that I already mentioned in the conditional probability statement. Probability of A and B, and the probability of B. I wrote that earlier, but I didn't really tell you what this meant mathematically. I gave you kind of an intuition for it. I told you it represents how frequently A and B both occur together. And you can find this number just by a little bit of algebra. If I multiply both sides of this equation by the probability of B, I get rid of this guy and I put it over here. And now what I have is an expression for finding this probability. All you have to do to solve these problems is find this and find this. And in the book problems, those are both given to you. It's like I said, the hardest part about these problems is knowing which probability formula to apply. Is it conditional? Do I apply the product rule, which is what this is? Or do I apply the addition rule, which we'll talk about next? Well, there's certain key words that you can use to help you figure that out. With the product rule, it's words like and or both. It tells you A and B occurred, or both A and B occurred. Those tell you that you're looking at you're probably going to apply the product rule. And this is the product rule, right? You multiply these probabilities together. And like I said, these will be given to you. So let's do an example from the text. Event A is that the driver is male. Event B is that the driver is safe. The textbook tells you that the probability, it gives you two probabilities. It gives you the probability of A, which is 0.5, and it gives you the probability of A given B, which is 0.3. And as soon as you're given both of those pieces of information, well, you can plug it into this equation. and immediately get your answer. But what do these numbers mean, right? So we've talked about 3 different probabilities today. We've talked about the probability of an event A. We've talked about the probability of an event A given B. And now we're talking about the probability of A and B. What's the difference between these 3 guys? Well, in this example, imagine I had a world, right, of all the drivers in the world. I could grab any driver in the world, and they're all in this circle. If I reach in here and I grab a random driver, the probability of it being a male is about 1/2, which we can get from intuition or also just the textbook, which gives you the answer. Now imagine I identified a subset of these drivers who are safe, and I put them all in this little circle right here. This is the same thing as restricting our search in the sample space to rows that are less than 4. This circle is the same thing as this circle. What we're going to do now is restrict our search to the regions where certain conditions are met. And the condition in this conditional probability is that the driver is safe. So if I pull only from these guys, the problem tells us, with the conditional probability, that if I pull a random person from just these guys, just this subset, the chances that it will be a male is about 30%. So they're different. If I pull it from the overall population, it's 1/2, because about half of all drivers are male. But if I tell you the driver is safe, well, now the proportions have changed, because males tend to be unsafe drivers. So the probability of them being a male is less than when we're including unsafe drivers as well. But now what does this guy represent? What is the probability of A and B, which is what we just solved for right here? Actually, we haven't solved for it yet. We're going to solve for it right now. All you do is plug these 2 numbers into this equation. So I've got 0.5 times 0.3, and it's 0.15. So the probability of A and B is 0.5, or 0.15, sorry. And what does that mean? Well, we've got 3 probabilities here. The probability of grabbing a male driver from the overall population, the probability of grabbing a male driver from just the safe population, and now this 3rd probability tells us if we go back to the overall population and I grab a random driver from in that set, what is the probability that that driver is both male and safe? We're no longer restricting our search to the region where drivers are safe. So the probability changes. There's a lot more unsafe male drivers out there than there are female drivers. So the probability of getting a driver who is both male and safe is pretty low. Because you're now selecting from a larger number of drivers. Yes, ma'am. Jenny.
Are the probabilities interchangeable? Like it's PB, but you put like.
Yes. Okay. So I apologize. What I should have written here is these are actually equivalent statements. So the probability of A of B times the conditional is equal to that, and it's equal to the opposite too. You can think of, right? You see how these are kind of opposites of one another? If you compare these 2 things, turns out they're both the same number. So whether you're given A or B, you can still apply this formula. Thank you, Jenny. Yes?
On the bottom one, the probability of A, B equals 3.
Hold on a second, I'm going to stop you right there. Because it's important that when you see the symbol, you don't think A, B. You think A given B.
A given B.
A given B. It's a conditional probability.
Okay.
Okay.
And does that 3 come from the?
It's given to you in the problem.
Okay.
Yes. So that's what I'm saying. These probability problems are essentially plugging and chugging, which is something my chemistry teacher used to say when I was in college. All you have to do is take the numbers from the problem, they're given to you, and put them in the appropriate formula. The tricky part is knowing which formula to apply. Because we just talked about 3 different probabilities here, and we've still got 1 more. So the question is, which one of these do you apply? Well, if it's a conditional probability, it will be very clear that certain conditions need to be met. It'll say something like A given B. If it's this type of probability, this where you apply the product rule, which is what this is right here, then the question will include some word like both or and, right? And then you know, okay, that's this type of probability, and I apply the product rule. And those numbers will be given to you. Once you've figured out which formula to apply, it's very straightforward, yeah?
Yeah, and so that P is given, that line.
P is the probability of A. Both of these are given in the problem.
Okay.
We didn't actually compute anything here.
Okay, I got it.
It's a very straightforward problem. I just wanted to introduce it conceptually with this idea of the world of drivers. Because it's important that you understand what these three probabilities represent. They're very similar to one another, but they are different. All right, now we're going to talk about, well, first I'm going to add this guy right here. So the third thing we're talking about today is the probability of A and B, and you should have a card which completes that equation. Next we're going to talk about the addition rule. So if the product rule tells you the probability of A and B occurring together, then the addition rule tells you the probability of just one of those things occurring, but not both. And we write it as simply the probability of A or B. And that is equal to the probability of A plus the probability of B minus the probability of A and B. Together. And what I'm interested in this equation are just these guys. So what I've done here, this equation, is this is a visual depiction of this equation. What this says is, I take A and B, and I add them together, and then I subtract the part that they have in common, this intersection in the middle. And what I have left is just the times that only A occurred or only B occurred, and they did not occur together. And that's how, this is the formula that you use to obtain that value. Like the rest of the problems in the textbook, these values are already given to you. You will be told the probability of A, of B, and of this. But even if you weren't, you could still find them, I hope. Ask yourself the question, how many possibilities are there? How many meet my criterion? How many possibilities are there? How many meet my criterion? And then you solve for this using the formula, using the product rule. But more than likely you'll be given the numbers. So it's just simply a matter of plugging them into this equation and figuring it out. Let's do an example of that. And this is going to be a really tricky example. This is going to be. These are the trickiest that these type of probability questions are going to get. All right, let's say event A is that Al is late. Event B is that Al forgets to sign in. And the question here is, what's the probability that on a given day, Al gets credit for attendance? Okay? So in order, and we're told that the probability of A is 0.2, and the probability of B is 0.1. Those are given to us, you don't have to compute them. The tricky part here is recognizing which formula to apply. And for the addition rule, this key word, or, is going to be your clue that tells you which one to use. So, let's think about this for a moment, because in order to answer this question, we have to solve for this guy. This is an example of what we call mutually exclusive events, which means that only one can happen. Because let's think about it. If Al is late to class, then he can't forget to sign in because he wasn't there. And if Al forgets to sign in, well, it implies that he was in class. So it's impossible for Al to both skip class and forget to sign in. Because as soon as one of those events happen, it immediately excludes the second one. And so we say they are mutually exclusive. And mathematically, we represent that with a probability of 0. So event A has some probability, event B has some probability, and the chances of them happening simultaneously is impossible. So now we have our three problems to answer this question. Well, kind of actually. Because the question was, what's the probability that Al gets credit? And what I've given you here are the two events that would make Al get no credit. So the probability of no credit is equal to the probability that he's late. Whoops. The probability that he's late plus, actually I'm going to write it out fully, is the probability that he's late plus the probability that he forgot to sign in minus the probability of both. As we were told, or as we just figured out, the first one is 0.2, the second one is 0.1, and the third one is 0. So that gives us an answer of 0.3. But that's not what the question was. The question wasn't, what's the probability that he gets no credits? The question was the exact opposite of that. It's, what's the probability that he does get credits? Well, these are binary events. And binary events allow us to do something in probabilities. If I tell you that two events, A and B, are binary, it means that one of them has to happen. And since the sum of all probabilities is always equal to 1, if I take these two, there are these, only A and B are equal. This is, the coin comes up heads or the coin comes up tails. And the sum of those two probabilities is 1. And I can always get the exact probability of just one of them by subtracting the other one from both sides of this equation. So I employ a little bit of algebra, and what I get here is the probability of A is equal to 1 minus the probability of B. And I can apply that to this problem. Because what I've just given you is this problem. You want the probability of credit plus the probability of no credit has to equal 1. Because those are the only two possibilities. You either get credit or you don't. And we're searching for this guy. So all we do is subtract this number from both sides, and what we wind up with is the probability that Al gets credit on any random day is 0.7. So be very aware of the question that you were asked and the information that you were given. Because there are times when you will be asked a question and then given information to figure out the exact opposite of what you were asked. But as soon as you know the value for the exact opposite that you were asked, you can employ this trick to figure out the one that you're interested in. Are there any questions about that? Yes, sir. Tucky.
So probability of A and B will be given?
Probability A and B will be given.
Okay.
But in this example, they were given.
Okay.
But even if they weren't, how would you go about obtaining them? There's two questions. Ask yourself two questions. How many possibilities are there? And how many meet my criterion? Do you remember the questions I asked you at the beginning of class?
Yes.
Those will guide you through any, if you're faced with a probability problem and you genuinely do not know what to do, just ask yourself those two questions. How many possibilities are there? How many meet my criterion? That's step one. Right? But again, in this example, you were given that information. So it's just a matter of identifying which formula to use and then applying it correctly. So you have the right formulas on your index cards. You should have 4 of them. The first one should read, how many possibilities are there and how many meet my criterion. The second one should be the equation for the conditional probability. The third one should be the product rule. And the fourth one should be the addition rule.